All right, good morning, everybody. Today is Thursday, so whether we have a snow day or not, I'm going to have this video for you to watch for this special cases. So for special cases, basically what we're doing is we're just looking at ways that we can factor quadratic trinomials, okay? But in certain circumstances, as you'll see in case 1 and case 2, and we'll talk about this, there are going to be very quick ways to solve them where you don't even really have to factor it if you know and kind of catch the pattern here. So let's just take a look here. In case 1, okay, we've done examples like this. You notice that it's a positive 9, right? So if we go to factor it down, we have v times v, and we have 9 off to the side. But then in the middle term, we notice it's negative. Okay, so this is a special case because we know that that means that both of these terms have to be negative. So we have negative 9 times 1, times negative 1, and negative 3 times a negative 3. And we know that these two would add up together to give me the negative 6. So it'd be v minus 3 and v minus 3. Okay, so this is a special case because if the last term is positive and then the middle term is negative, we know it has to be two negatives. Okay, the other thing is it's a special case, and we'll talk about this, because this is a perfect square, and so is this term. And what I mean by perfect square is, remember that you have 1 times 1 equals 1, 2 times 2 equals 4, 3 times 3 equals 9, 4 times 4 equals 16. So these are all perfect squares. So if you see that the last term is a perfect square and that the first term is a perfect square, okay, there's something to do with the middle term that's going to allow us to look at it this way. Now, the other thing is we can write these two, okay, since they're the exact same parenthesis and they're being multiplied together, we can write it as v minus 3 squared, okay? All right, so now let's take a look at case 2. Kind of a similar case, right? You have a perfect square and a perfect square, but notice that there's no middle term, like 2m or anything like that. So we're going to look at it like this. How do you get negative 4? Well, negative 4 and 1, negative 2 and positive 2. But we know that there has to be no middle term. So that should tell you that it needs to cancel out. Well, what two numbers, or what two factors over here, if you add them together, would cancel each other out? Would be the 2 and the 2, which again makes sense because 4 is a perfect square, right? So the negative 2 would be a negative 2m, and the positive 2 would give you a positive 2m, and so those would cancel out. Okay, one negative, one positive. So when you only have two terms like that, there's no middle term, and the last term and the first term are perfect squares, 1, 4, 9, 16, 25, 36, etc., then it should be a very simple factoring process. So what we mean by those are basically this. You can factor normal if you want. If you're not catching the pattern that I'm putting down, right? You can definitely factor normally. But there are perfect square trinomials where if the first term is a perfect square and the last term is a perfect square, then the middle term should be 2 times the first and last term. So twice the product of the first and last term. And then it's just going to be this answer. So that's kind of this example. See? Negative, positive, perfect squares, a minus b squared. So if a was v, b was 3, a minus b squared. Okay? So all that means is that when the middle term is twice the product, ooh, that's not how you spell product, of the first and last term, okay, that's how you know it's a perfect square trinomial, okay? And then in case number 2, which was up here where there's no middle term, that's called the difference of squares. So what it means is you have a perfect square minus the constant, which is also a perfect square, then it will always separate into a minus b and a plus b. So what we mean by that, again, is if you go back to the example we just had, okay, this was equivalent to m minus 2, right? Because what is b squared? Well, that would be 2 squared. Well, what's 2 squared? 4. Okay, so you have to take the square root of both, right? And the square root of those would be m and 2. So you'd have m minus 2 and m plus 2. Okay, so that's when the middle term cancels out. And the first and last are perfect squares. Okay, that's what they mean by that. So when the middle term cancels out, there's no middle term, and the first and last term are perfect squares, you have what's called the difference of squares. Now again, you can factor this normally if you want, but it'll be a lot quicker if you recognize that it is a difference of square and you can just write the answer down. You don't even have to factor it. Okay, so let's go through some of these example practice problems. So right here, we notice that the first term is a perfect square, the last term is a perfect square. Okay, so the square root of 16 is 4. Square root of x squared is x. And the middle term is negative, so that tells you it should be x minus 4 and x minus 4. Now, just to check our work, this would be a negative 4x. This would be a negative 4x. Negative 4 and negative 4 would definitely give me a negative 8. Okay, so our solution here would be x minus 4 times x minus 4, or x minus 4 squared. Okay, same thing over here. This one's both positive. Perfect square, so the square root of x squared, square root of 25, this would be x plus 5 times x plus 5, which would be x plus 5 squared. Okay, these next ones are difference of squares, which means they have to have opposite signs because the middle term has to cancel out. So you would have x plus 5 and x minus 5. Okay, because 5 times 5 gives you 25, and the negative times a positive gives you negative, and then the negative plus a positive would cancel it out. So our solution there is x plus 5, x minus 5. Another difference of square, perfect square, v minus 4, v plus 4, because there's no middle term, so it's got to cancel. Right? Down here, same thing. Even though it's a 4 out front, 4 is a perfect square, 9 is a perfect square. Okay, so take the squares. You're going to have 2x plus 3, or I'm sorry, 2x minus 3, because it's a minus here, and 2x minus 3, because again, what's the square root of 4? It's 2. What's the square root of 9? 3. 2x minus 3, 2x minus 3. And then, again, you can check your work. This would give you negative 6x, which gives you a negative 12, right? So our answer here, 2x minus 3 squared. Okay, difference of squares here. Perfect square, because 3 times 3 would give you 9, and 7 times 7 gives you 49, but notice there's no middle terms. That means you have to have a positive and a negative. So there's your solution on that one. Okay, 7 times 7 gives you 49, 3 times 3 gives you 9. Plus, minus, no middle term. Okay, sometimes it won't look like that, right? Like this one's got a negative, so you're like, oh, it's a difference of squares, but these are not perfect squares. However, you always have to factor out the GCF first. So if we factor out the GCF, which in this case would be a 3, that leaves you with 4n squared minus 4n plus 1. Well, now the first and last term are perfect squares, 4 and 1, right? So take the square root of both, which would be 2n and 2n. Middle term is negative, so that means it's negative, and 1 times 1 gives me 1. So our solution here, 3 times 2n minus 1 squared. Okay. Same thing here. Let's look for a GCF first. In this case, we can factor out a 2. Gives us 16p squared left over minus 1. Well, that's a perfect square. That's a perfect square. Okay, so it's a difference of squares, which means it has to have the middle term cancel out. So we have one positive, one negative. Square root of 16 is 4. Square root of 1 is 1. Okay, so again, notice how quickly we don't have to do like the guess and check and pull it off to the side and all that. You don't have to do any of that stuff if you just recognize that this is a difference of squares. This is called, if you go back up, you'll see it's called perfect square trinomial. Okay, for number 7. All right, number 9, difference of squares. Perfect square, but you can factor out a GCF first. Okay, again, still perfect square, but difference of difference of squares. So one positive, one negative. Square root of a squared is a. Square root of 4 is 2. Okay, same thing here. Okay, what can we take out? Let's see, not 8, because 8 does not go into 50. Not 4, because 4 does not go into 50, so it's got to be a 2. So 2 out front. Easy with 4k squared plus 20k, plus 25. Now again, these are perfect squares, so the square root of those would be 2k, 25 would be 5 and 5. They're both positive, right? So that would make these both positive. And since I have the same thing in both parentheses, we would rewrite it simplified. Okay. All right, so here's what I want you to do. Go ahead and try the more practice. I'm actually going to post the answer key for this, and then you have your exit ticket. All right, so I'm going to post the key and exactly how to do these. Okay, it'll be on Canvas. Take a look. Do that first before you try the exit ticket on your own. Okay, if you have any questions, shoot me a message on Canvas. Again, these are called special cases for a reason, so hopefully you're able to identify that they are perfect square trinomials and difference of squares. Okay? All right, guys, I'll see you in class.